We have with us today Vandi Verma, who is a graduate of the Robotics Ph.D. program here in 2005, working with Reed Simmons, who's back in the corner there. I think on software fault detection, is that right? She went from CMU to JPL and got excited about operating robots on Mars. I think maybe you're excited about that. But I believe operated all of our robots on Mars, right? Spirit, opportunity, curiosity, perseverance.
Yeah, and Ingenuity. Just
And
Ingenuity. Just left Sojourner. I was still at, actually.
Not a Sojourner. We were born at that point. All right, so super exciting to have Vandi here to tell us about operating robots on Mars. And also, I think you're running robotics for JPL now too. So all about robots.
Co-running. So as I was saying before, I was going to talk about Mars robots and some of the robotics at JPL. And going to just, I thought I'd start, some of you know, but JPL is a little bit like a lot of other organizations. We have two parts. One, just like what's the difference between how the Mars missions work and how robotics works and why those are related. So just initially jumping into a little bit of that. And so this is just like the banner for robotics. So at JPL, we have what we call a line organization. It's a lot like departments at a university. You may have, computer science and robotics. So that's, we deal in robotics with everything from early stage development of concepts to actually doing the research prototypes and working on the actual missions and operating the missions. So there are about 200 projects we have in robotics and the tasks of all kinds of different sizes and scales. And generally, this is where all the people are housed. So everybody belongs to some, essentially, line organization. And then the other one is a mission, like the Mars, a robot would be a mission. That generally involves people from multiple different organizations working together. You need the scientists, because most of our missions are science-based, so who will look at where we are going, what location we want to land at, what science we want to do. The people who work on the parachutes. So robotics is an element of a mission, and so most of the Mars missions have had robotics in it, but they have other aspects. So these are on the scale of thousands of people, and robotics is on the scale of we have over 200 people, but it's focused on the robotics aspect. So I have a role in each of these. So like Dave was saying, I co-lead the robotics organization, and then I work in the mission side, specifically on the Perseverance mission. So I was going to go into the details based on those two aspects of it. So starting a little bit with the Mars robots. So we've had 10 total missions that have successfully landed on the surface of Mars. The Viking landers, and they've been 6 robots, and 9 of them have been from JPL, and now we have one from the Chinese Space Agency, Zhurong, that landed on Mars. So what we've typically done with the robotics on the Mars missions is, so far, we're sort of looking at new aspects, but has been kind of focused in 4 areas, which is mobility and navigation. So generally, the rovers kind of really changed things because you weren't stuck to a spot. You could go do sign at different spots. So there's a lot to do with mobility and navigation. And I'm going to talk about that because when you're moving a vehicle to different parts, there's a lot of hazards and there's a lot of potential. And then the robotic arm, because mostly we go to Mars to deploy instruments in close proximity, and you want to be able to put them on very specific targets. So we have robotic arms, which have a turret at the end of it with a lot of instruments packed on it. And then the sampling system. Lately, with once we were able to do a lot of remote science, you want to go and actually collect material, either analyze it in situ or go and bring them back, as Perseverance is doing. In the case of Perseverance, here I'm showing sort of inside, this is the outside arm docking with the body of the rover. There's a bit carousel, and inside it, under the rover, is a second robotic arm and a system that kind of manages and seals tubes. So there's like a second robotic system inside the rover. And they do a handoff through this bit carousel. So the external arm docks with it and has to do that autonomously, and then will sort of switch around to select the different tubes. And then, of course, we have, with this mission, a helicopter. So we are also have a lot of missions now that we're looking at, which are multiple robots that gives you a lot of new possibilities. And with aerial robotics, there's another. This is kind of one of the flights. That video was taken by Perseverance looking at Ingenuity on Mars. And so the next, it's sort of, let's advance this. So in terms of Perseverance, it's been a really successful mission so far. It's collected, at this point, 22 samples, and it's twice the rate. So it's sort of very difficult to collect samples because the moment you're sort of interacting with surface, very odd things happen. The very first sample we collected with Perseverance, there was nothing there. It just, the whole thing pulverized. So even if you have been on Mars for decades, when we encounter new material, interesting results happen. So sampling is always a challenging problem because you're actually trying to interact with surface. That is novel. We're going there to explore. So it's been very successful. And then autonomous driving. So it's 88% of the driving, which is far more than any mission, has been autonomous. So up to this point, we've actually, as of now, we've driven 19 kilometers in just the last couple of days since I made these slides. But it's driven quite a lot of distance, and it has a lot of records for Mars in terms of driving on Mars. And what we are limited by in terms of driving in a day is actually the time to drive. So you want to maximize in that time how much you can drive, because we still rely on daylight, both for navigation, but also just heating. Mars is really cold. If you spend your energy heating, you're going to have less energy to drive. So you try to drive in the warmest part of the day. And it's exceeded the prior record. The prior record was actually set by Opportunity all the way back in 2005. And we've, at this point, actually, it's exceeded it 23 times. So it's very consistently that we are driving hundreds of kilometers a sol, which was not very common before this. Curiosity never exceeded Opportunity's record. So it's sort of, it's sort of not an easy thing to do on Mars. We also now drive multiple sols. So instead of just in a one sol driving, we'll tell it for the next, over the weekend, once we get off Mars time, we do our missions earlier, we're in sync with the Mars clock. And then we take our weekends off after a couple of months of the mission. And so on Friday, you'll tell it what to do for 3 sols of a plan. And it just continues to drive through the weekend. And then you come back on Monday. And that's where we got like a 700-meter drive. And at the end of drives, you kind of don't know what you're going to see. But I'll go into it. We do autonomous targeting because you want to find interesting science features, but you don't know them a priori. And so we're using that. And before this mission, we actually didn't know if we could fly on Mars because the atmosphere is like 1% of the Earth atmosphere, and it's such a lightweight vehicle. Ingenuity weighs 1.8 kilograms. We've now had 50 successful flights. So kind of really, it's opened up a new way where we're now starting to think of aerial mobility as like a potential for actually basing science missions on. And so that's kind of what is very sort of unique about a lot of the missions we do. It's driven by the science. So why you're doing it is to go solve what the science problem is. And robotics is a means to the end. So the robotics, it's sort of not about driving far or driving fast. It's about like what's going to accomplish the science. This is Jezero Crater. This is where we wanted to go with Perseverance. And part of the reason is in this crater, you see the little fan of a delta. And we're looking for signs of ancient life. And deltas are very likely to harbor signs of life. And so this was where the scientists wanted to go. Previously, we couldn't really go to locations like this. Here, I'm showing in the small inset the landing ellipses. So when you land on Mars, there's just this enormous uncertainty of where the parachute's going to deploy and how the vehicle's going to end up. They were just really long, 80 kilometers, in previous missions. And with Perseverance, we were able to reduce it quite a bit because you use autonomous capability so that even as we are coming into the Mars atmosphere, it's able to use the capability of computer vision. It's doing landmark detection and detecting hazards to divert away. Because this happens, all of the landing from the time we enter the Martian atmosphere to we land is about 7 minutes. And there's no, the signals, by the time we get the signal on Earth, the vehicle's either landed or crashed. So here you'll see as it was landing, this is actual data from Mars, it was detecting that we were headed to a hazard. It ended up doing a divert. So it had the capability to do a divert and diverted us away. So we were headed for the delta. This is the area, and it diverted us away from the hazardous zone once it converged on a solution onto the other side of the hazard. It actually had multiple solutions and found that this was slightly better. So here we are trying to go to the delta, but we ended up landing all the way over here. So now we were going to have to drive all the way around to get to the prime area of science interest. Once we got here, the scientists were like, well, we're in the crater flow, let's do some science here. So we did some initial science here in the mission, and then we have 3 primary campaigns. They sort of characterize what the main goal is. So in this, it was the crater flow we are sampling, and then did a rapid traverse, which was mostly like, get me from one point to the other. And then in the delta, we did another science campaign. And on this chart, I'm showing this is some of the real examples. So here on Perseverance, you're seeing all the instruments, right? It carries 60 kilograms of instruments. And that's kind of why the robots are that large. Perseverance is the size of a little car. The mast is 7 feet tall, so a lot taller than me. And here are the sites at which we sampled in the red crosses, and the other instruments were deployed in all the other colors. So really, you're seeing that scientists were interested in this location and this, but really they're not that interested in what lies in between. And that's kind of where robotics gets really interesting, is where the problem we wanted to solve was when we really want to do a rapid traverse, go really fast. And then when you're doing the sampling, focus on the sampling. So it's two different switching modes. And we were able to do most of about 95% of the driving there was all autonomous, because we didn't have to worry about precisely getting to locations. And that was a 5-kilometer drive. And the challenge is you only get to talk to the spacecraft once a day. So the communications, the way we communicate is we talk once a day because it can take up to 24 minutes. And we don't have exclusive deep space network access. We are sharing it with dozens of spacecraft. We get to get data down multiple times. But you're going to have to send the plan for whatever it's going to do for the entire sol and utilize as much of the time that it has available with energy. And so the only way to really do it is with autonomous navigation. Because if you're going to have humans direct it, we can't see past the horizon. Because the orbital maps don't have accuracy to tell us hazards. Even the scale of a vehicle the size of Perseverance, there are still hazards we can't see from orbit with the accuracy we have. So you need to see from the rover's point of view. And here is a graph showing on the x-axis the sols up to about a sol 753. And on the x-axis, you're seeing how many kilometers. And these are the different modes. So this one, orange, avoid all, is fully autonomous driving, where the vehicle is using its cameras to take images, do local hazard avoidance, and then pick a path through it. And then we have other modes. Guarded is where we tell it precisely to follow what we directed it to do, but avoid hazards. So it's still following a much more prescribed path, but autonomously checking to make sure there isn't a hazard. And then there are other gradations with visual odometry. But a large part of this has been autonomous, and this is the rapid traverse where you can see we were just focusing on the driving. And that's how, in less than a month, we were able to get that entire distance. And we get about a couple of hours, 2 to 3 hours a day to drive. And we're trying to increase that by doing some onboard planning now, which will get us more time to drive by more precisely managing the resources. That's something we're going to deploy in August on the spacecraft. This chart is a little bit, dense, but at the same time showing these are all the rovers that have had any form of autonomous capability in the column. So there's Sojourner, Spirit, Opportunity, Curiosity, Perseverance, and what we know of Jurong. And you can see that the autonomous driving with Perseverance in the top row there is significantly more than any of the missions before it. So it's done, almost 14 kilometers with, this is actually older data, we have much more than that now, autonomously. And if you look at the actual hardware, Perseverance looks a lot like Curiosity. When we are doing the flagship missions that are on the scale of Perseverance, these are decadal programs that the National Science Foundation decides once a decade. They do a study and say, what are the things, just a handful of missions that could really change science the way we know it? And we invest in those to do these missions. But they really need to succeed. The risk that you can't have major problems mean that you get nothing out of that investment. So there's a lot of heritage. So Perseverance and Curiosity, if you looked at them at a distance, you couldn't tell them apart. They are so similar. They have the same rocket bogie design, the same motor controller, and actually the same processor, which is really slow. It's a 133 megahertz RAD 750. And partly because it's a radiation-hardened processor, and the consequence, we do these matrices at NASA where we have risk and consequence. Some of you might be familiar with these. And they're a really important part of the analysis of saying, when I'm doing this mission, and they could cost up to $1 billion, am I actually have a high probability of getting the science return that we're making this investment in? So with Perseverance, we were like, we wanted to drive a lot further, but these were our constraints. How were we gonna get this significantly improved performance? And so this is where I think being on Mars for so long gets really useful. We can look at the data and say, what are the points that really, really are limiting us? And you could go from first principles. And this was one of the big changes for me going from like university to working at NASA is you rarely ever get like a full clean slate. So constraints are really a big part of the NASA missions, right? Weight, energy, and also showing heritage or link to showing that you have lower risk. And so how do we go do this? So instead of just changing the computer, we actually added co-processors. So Perseverance has a second computer, which is also a RAD 750, but is dedicated to the processing for the navigation. It was actually used during the landing. We also do the stereo computing, which is some of the most expensive computing in hardware in an FPGA. So we did that, improved the cameras so we could have fast exposure, wider field of view. And then once we landed with Curiosity, one of the reasons we don't use autonomous navigation is we have these planetary scientists who specialize in Mars, and they were like, this is what the terrain's gonna look like. We had these tiny rocks, not a geometric hazards, because they're really small on the scale of 5 to 10 centimeters, but they were very sharp. They're made out of volcanic material, and they started piercing the Curiosity wheels, and we have holes in the wheels. Now we had to navigate around them. So you either make your algorithm really complicated so it understands what a ventifact is and navigates around it, or the approach we took with Perseverance is you just make the wheels better so they're not impacted by that. So that's another part of the looking at the whole system and saying, where do I solve this problem in a way that has the highest probability of success? And here too, each of these wheels are made out of a solid piece of metal, and they're so expensive. So we 3D printed wheels of lots of different sizes and patterns and tested which one would work, driving them kilometers in the Mars yard. And we're able to select between them without actually investing in the actual metal wheels. And then, of course, we improved the path planning where Mars is very sandy, and slip is just part of what you're going to get as you're driving. Your odometry is not going to tell you precisely where we are. We used to stop, think what the hazard is, and navigate around it. Now we actually do what we call thinking while driving. But this means you have to predict what slip you're going to see, where when you have your next step interact, it's going to merge. And so all of that was algorithmic improvement. We do much better path planning search. So we're not looking at a limited set of arcs. It's a much more denser tree. And we're also actually not treating the rover as a disk as we used to on previous missions where any orientation was not a hazard. We now can straddle rocks and are aware of what the sort of kinematics of the wheels are. Another part is, after we drive and you're swerving around obstacles, it would end up at different headings. So now we do autonomous turn for communication. You know where Earth is. And after it's driving, if it can't turn to Earth safely, it'll continue driving till it gets to a point where it can turn to Earth. So it can communicate with Earth. And then we also autonomously find the sun, because our uncertainty increases as we are using gyros and IMUs. And so it'll stop. Once it's like, my uncertainty's gotten too bad, I'm going to stop, go find the sun, know, and reduce my uncertainty to a certain level, and then continue driving. We still don't go to zero. We do that once we have Earth, and that's a part I'm going to talk about is still done with Earth in the loop. Another part was, this just gives you a sense of like how the sorts of things we look at to improve the algorithm. The actual generative path as to what path we'll choose, and this is the actual tool we use to drive at Mars. So we use a very high-level graphical tool. This is a mass cam image taken. As you see, we have so many occlusions. There are lots of holes in the meshes. So in the near range, a human is sort of telling it, here are the waypoints with this way disk that you drive, and that's that initial part of that drive. And then after that, using an orbital map, because I can't see from the rover's viewpoint. But instead of having the rover know all the various constraints for the path on the ground, we actually do the waypoints from Earth, and then you're seeing the actual path that's fine simulated in cyan here, where it's able to, on Mars, divert around the hazard, but it still use the guidance of the waypoints we lay out. So you don't have to sort of look at all the various factors we put in. We have a radar under the rover that is collecting measurements, and the scientists sometimes have preferred paths. You can make all those measurements. This is the video of, these are the images that it uses to do the autonomous navigation. This is 200 times sped up. This is from the this is from the vision compute element, and they are black and white images. And this was an actual drive on Sol 210 that we did to give you a sense of what sort of the autonomous algorithm is doing to navigate. And this was an actual turn for calm at the end of it. And then this is another image to give you a sense of the drive. This was the Sol 750. We did a 347-meter drive looking back at the terrain. Go ahead. Yeah.
So what restricts the speed? Is it that the motor, is it like kept slow for safety reasons, or is it that the motor capacity is, it's already running at motor capacity? What is
Yeah,
that?
that's a great question. So the question was like, what limits the speed of the rover? And so the mechanical top speed of the rover is really slow. It's 4.2 centimeters a second. And it's the same as Curiosity. Perseverance hasn't changed. And a lot of the reason is the complexity. It's the motor controller that limits it right now, but also just the overall design of the system is based on constraints that would mean that, you know, once it starts to get faster, you need to worry about improving the computing and the motor controller speed, and that's what we're limited by right now. So that's the top mechanical speed.
So the motor has the power, but the controller is operated at a lower frequency because of...
So both the motors actually, they weren't designed to have more power than that, and the controller is designed to be optimized for that. And some of it just has to do with, you know, do you gain a lot by making it faster? And actually, that's a study, again, the trade-off there was that we weren't going to gain so much. We can actually just go further with that speed itself. And so right now, it would be nice to go faster, but that was also the inherited design, and they didn't want to change that with Perseverance. But some of the future missions we have will go a lot, are looking. So we have a mission in the future going to the moon that will be driving at much faster rates because we want to go kilometers in a day. So the Mars rovers has been limited by that, but that's not a general limitation for space missions. So this is again showing a multiple Sol drive, and I'm just going to go faster through it since we have more limited time, showing that this was around Zeta. This is a 500-kilometer drive we did over multiple Sols. So we had multiple days to drive over it. And then just giving you a sense of the autonomous science. So once you're driving, at the end of a drive, you may get a terrain like this, and you don't have Earth in the loop. What should you target? So this is a case where we take a wide-angle image with a nav cam, and it picked, you're seeing this, these two, it actually picks a lot of targets and said, these are two targets where these would be interesting to take imagery, taking the wide-angle field of view with a narrow field of view imager. And so this is an actual image from Perseverance from Sol 449, where you can see it's about, this is the scale here for 2 centimeters, taken by Aegis autonomously, where it's taking the remote micro imager, which is a telescopic imager, and it's able to get really fine mineralogy and geochemistry to study. So you're able to actually, because you're autonomously doing it, you're able to detect interesting rocks rather than just get sand. And then, of course, there's aerial mobility, where there is this restriction where Ingenuity, the helicopter, only talks to Earth through the rover. So it needs to have line of sight to the rover. So when we're doing the planning for the rover, we need to make sure that the Ingenuity is, we fly and drive on the same days, because otherwise we'd be too slow. So you need to make sure that when it succeeds or not, can it still talk to Earth? And that COM map helps us do that. When we were going around, Ingenuity was not going to be able to keep up. So it actually went right across and flew across so that it was going to be able to get to the delta at the same time as the rover. So we will plan these paths. But it's, you know, a very light vehicle, and it was designed to just, it's a technology demonstration where sometimes we want to experiment with something that is more risk, and that was Ingenuity. And here you're seeing these flights where once we got to the delta, it was the Martian winter, and the temperature at night started dropping really low. So this is, you know, the actual, and this was the predict. And we had predicted that we would get really low because, you know, this is well past its mission. But we sort of, on around Sol 426, we sort of lost contact with Ingenuity because it went into such a, it essentially froze. And so we weren't able to contact it. And then it warmed up eventually, booted up its processor, and would come up. But when that happens, it's completely lost track of time. And now it doesn't know when the rover is going to try to communicate with it. So now what we've done since then, the temperature started to get better. And we still do it today. Since then, which has been all of the flights since that flight, we have a phase in the morning where we do what we call a capture, where we hunt for when Ingenuity will be up. We've gotten really good at it, so we only have to do it for about an hour. We capture it, and then later on, there's the optimal time to fly, because you don't want to fly when the winds are too high, but you also don't want to fly when the temperature requires much heating and doesn't have enough power. So then we fly it the next day. It'll come again, it'll forget what time it is, we capture it and fly it again. So that's what we're doing with Ingenuity these days. But it's doing well. Here's a video of a recent flight when we're on top of the Delta. This is on the Delta, and you'll see a little Ingenuity. This is the 47th flight, and this is a video taken by Perseverance of Ingenuity flying. And so, there's a little bit of pointing accuracy that you have to get where both are uncertain. You're taking it with the mechanism and pointing it at a flying vehicle on Mars. So, it's still flying, collecting imagery, letting us see over areas to see, is it worth investing in the rover actually going over to a certain terrain to navigate? And certain areas we've decided were not worth it because Ingenuity flew over them. And then, I'm going to go a little bit faster. This is talking about the samples. So these are the sample cores we had collected once we got to the Delta and cored there. We've actually collected another one since, but it's a fairly rich and interesting sample set. And the scientists were like, this is amazing. You look at it, you look at all the different, what you're looking at here is we core into the ground about the size of a chalk, and we pull it out and we hold it up and we take an image of it. We have another camera inside the rover's belly, a cache cam, which takes a much higher resolution image, and then we seal it. We have different stations that we move it to weigh it, seal it. But this is the cross-section image that you're seeing of each of those cores. They were like, there's a possibility when you have a mission on Mars, which is such a high-risk environment, could die at any time. It would be really sad to have these really amazing samples inside the rover, and now it's not functioning anymore. So the plan has always been, and this is the plan for the Mars sample return mission of which Perseverance is a part, that Perseverance, which is the Mars 2020 mission, launched. It's collected tubes. To hedge against anything happening to it, we drop these tubes once we have an interesting enough sample on the surface. And another mission's going to launch, which is the sample retrieval lander. On the lander are going to be 2 helicopters that have a robotic arm and wheels on them that can then go fetch 1 tube at a time and bring them to the lander as a backup. In the prime plan, Perseverance keeps collecting, and then it directly transfers to the lander, and then we're also sending a rocket on this lander to Mars that'll launch and bring back. So we were ready because the scientists said, this is so interesting, let's drop these on the ground so we have something to bring back no matter what happens. And so this is showing the depot we created on Mars, where we've dropped the samples. We take them from inside the rover and drop them at very specific locations. This was a challenge because you have to make sure that the future helicopter can navigate. This is not a hazard for Perseverance, but Ingenuity weighs 1.8 kilograms. The helicopters that are going to be on the next mission weigh 2.3 kilograms. So the entire mobility and manipulation system weighs 150 grams. And so that vehicle is skid-steered, and it has to navigate around these obstacles. And so we had to lay them out so it could successfully do that. And now this is the part of the Delta you were seeing. So we are climbing up here, and then the mission just continues on. So as you see, we're going to drive considerably more distance than we have covered. And the plan is to meet with the sample retrieval lander somewhere around here where it's going to land. We're going to transfer the samples. And this is a video showing the plan for the Mars. I usually turn the sound off so you can see. So this is essentially that second spacecraft that is going to get to Mars. And we're going to take the samples that are, that's Perseverance, watching at close proximity, watching the lander come down. It's massive. That lander is really massive. And then it's going to drive up to it. And once it drives up to it, there's a 7 degree of freedom robotic arm on the lander. And that is going to then grab the tubes out of Perseverance and put it. So we have a canister orbiting canister in which it stacks all the tubes, it closes, and closes the lid. And then there's another robotic mechanism that will then transfer those into the rocket. And then the rocket launches from Mars. And then we are going to go into orbit around Mars. There's another spacecraft we launched actually a year earlier that's orbiting Mars. There's a robotic arm on that spacecraft that is we're going to eject that canister. And then there's another spacecraft that is going to capture it and grab it in Mars orbit. So you see it's just kind of a lid that comes across and closes up, and it's grabbed that sample. And once it's in there, it's going to fly back to Earth, and then we are going to enter Earth's atmosphere and bring those samples back to Earth. In fact, even when they come back to Earth, we have very strict contamination requirements. There's going to be robots that sort of manipulate it even on Earth in the laboratories and study it. So that's sort of what's the mission that we are sort of completing, and these are the various elements of it. So Perseverance is just the first step of this mission, right? And then I was just going to talk a little bit, as I said, about some of the other actually some of the challenges on Perseverance, and then I'll touch a little bit on this. I'm going to do it really fast. So we've been plotting, like, what are the faults we've had on Perseverance? Like, what are the things where we've actually had, and how can we actually get even better performance? So this is a plot, and one of the things is there are times at which we don't find a path. And this is that drive I showed you around. So this is the CETA region, and we were driving multiple sols around. If you see the uncertainty, the blue, this area is showing how the uncertainty grows as it's driving. From the ground, human operators, sand we don't detect very well. So we tell the robot from the ground, these are areas that are keep out zones in red, stay away from them. But as it's driving, its uncertainty is growing, so it must navigate through it with its uncertainty. And it couldn't find a path, and that's why you see it. Try to find a path and hunt around it, and it can't. What we are looking to do now is do global localization on board, where at the end of the drive, it's going to use the global map on Mars and then take images surrounding and see where it is and do the localization and reduce the uncertainty. If we did that, our uncertainty would be to the scale that we'd be able to make it through those paths. But this is very computationally expensive, and that's why we didn't do it in the first place. And so how do we do this? So what we're looking to do is Ingenuity, actually, because it was a technology, has a COTS processor. It has a much faster processor. It has a Snapdragon on it, and it has more processing power than all the robots we've sent to Mars combined. That little helicopter, right? So the question is, maybe we can make use of this. There's a second computer on Perseverance which helps Ingenuity communicate with Perseverance. It's mounted on the rover. So what we expect to do is use that computer to do the rover's processing essentially as a computer for the rover by shipping the images there, do the computation, and send the results back for the global computation. There are a lot of challenges with data rate and all because it was not designed to do this, but this is something we're working on. In fact, interns are working on this because when you're working on these kind of ideas, this is the sort of thing where we often have students work on because there's high reward, but there's also like potential for lots of challenges. So. But the challenge is, there's a lot of difference between that global map and the viewpoint of the rover. There's occlusions. And so it's not an easy problem when you look at it, and this is a video showing, this is an actual image from the end of the drive. There's got artifacts and holes, and you have to register it. A lot of things look the same. So that's one problem. Another one is path planning, where we are laying these viewpoints from the ground, looking at approaches where even on the ground you could have some automated planners generate the path. Of course, we have a lot of planners, but none of them have been as good as the humans. So mostly humans are like, that's a suggestion, I'm not going to use it. So coming up with path planners that could actually factor in all of the various things that we worry about when we generate the paths. And then, so most of the sampling is, once we drill, collect the core, it's all autonomous, it all happens. We take the images, all of it, because it's free space motion. Anything we do in free space is actually, even with all the uncertainty, is very doable. It's that contact with the surface, where we're going to drill, is where there's a lot of uncertainty, and we spend a few sols just figuring out what location on the surface that the scientists want. And it involves imagery from various different context imagers, and so this is another part where we want to do on board, where we would like to, on board, take the images and determine if we can meet the clearance assessment. The arm manipulator, it weighs 100 kilograms. It has a lot of droop and uncertainty, like 2.5 centimeters end to end. instruments have requirements at a millimeter scale. So how do you go from there? We do it with Earth in the loop because we use tools on the ground. We'd like to do it on board. So that's another problem we're looking at. And then, this just shows the commands. This is actual commands we send to Mars for arm, flying, sampling, mobility by Sol. And you'll see, we send hundreds, sometimes thousands. And this is the sampling. It's fairly autonomous, happens in a day with some arm and sampling. But there's a lot of arm work happening ahead. That's the kind of thing where we're taking a lot of time here studying where we should drill. And then you see the spikes, which is where we sample. And we'd like to reduce this and do this more autonomously. This is that rapid traverse where you see we're just driving and flying, where we weren't doing any sampling. And then I was just going to end with some of the ongoing flight projects and work. So one is this Mars sample return. We are very actively working on this. One part is the arm. So this arm is being developed, the hardware is being developed by the European Space Agency, but the arm software, which has to actually connect and dock with Perseverance and get the tubes and put them in the canister, is all work that we're working on. It needs computer vision because we need to do all of the stuff of taking the tube and putting it in there without Earth in the loop. Once we have a rocket on Mars, there's a clock ticking of when we come back. That mission's going to be far more constrained in time than any of the previous robotic missions. Because if we don't launch, it's not reliable to know if the rocket will still work past a certain stage. So we really need to launch. That entire mission on the surface is going to be 180 sols. A very short mission, has to be mostly autonomous. And the helicopter so these are the tubes we've dropped on the surface. Ingenuity was dropped from under Perseverance, so it sort of fits under the rover. Same scale, again, the same dual rotor concept, but now we have a manipulator to grab. This is, again, something we're working on. This is a skid-steered vehicle, all kinds of interesting problem. Very actively, actually, we have interns helping with this a lot as well. So this is another task. The other part is the robotic mechanism that has to take the canister and put it in the rocket. So that's also work that we're doing where we have to, and it's very simple, but it really has to work because that part of it, if it doesn't work, then the rest of it doesn't really matter. So that's another task. And then I was going to shift to a little bit of completely different missions. This is Cadre launching, I think, next year, which is multiple robots going to the moon. And from multiple vantage points, it's doing a multi-static ground-penetrating radar to build a terrain characterization. And then there are research tasks, tasks that we are looking at for future missions. And we have a couple of hundred tasks, but I'm going to give a few examples. With Ingenuity, we're just taking images. It has opened up a new area, and we'd like to take payload. So this is the Mars Science helicopter, which is a helicopter on Mars that'll be able to carry a payload, so it's going to fly with science instrument. There's all kinds of stuff where you're like, how do you get such a heavy? So they're looking at mid-air deploy, where it doesn't actually land. As we're entering in, it deploys into the atmosphere and various other things. This is a field test we did recently in Nevada with a Venus balloon. So launching a robotic balloon to Venus, and there's all kinds of characteristics with something that's going to survive the Venusian atmosphere. This was last summer. We always have somebody in the field. We have a field test somewhere or the other. This was in Alaska, where we had the Europa lander with its robotic arm testing. When you're going that far out to Europa, we're not going to be able to talk very frequently, and it needs to be autonomous. So autonomous sampling in ice. And then this is a project where we're developing a snake robot, which some of you have probably seen, to go to Enceladus. So the decadal survey that came out this year really highly prioritized the ocean worlds because the probability of finding life is so high. So a snake robot to manipulate and go into the vents in Enceladus to study. This is called the EELS project. Very active project. This has a lot of students and people working on it. And this is an example of one of the tests where we are testing it on ice close to JPL. This is one of the current models. Actually, it's evolved even since then. I think this is slightly outdated. And they have another field test, I think. We have a ski resort close by, so they get to go to the ski resort, and people are like, what is this? Is a snake robot out here? And also they were in Alaska last year and are going to go back for that. So I was going to, because I want to just end with, since the last time I came here, it's like we have this. If you want to look at more information, you can just take a picture and there's a QR code. Also, it has a link to at least all the current job opportunities. We don't have internships there yet, but we hope to as well. So you can, get updated information as they come about rather than sort of looking at something static. So yeah, that's all I had, and happy to answer questions.
So do you see in the next future more helicopters instead of using rovers? Seems like the mobility is going to increase, however, like the weight is going to also be a problem there. But you see that there is where we are going with the new Mars missions?
On the next Mars mission, we definitely have the helicopters. I think you're going to see a combination because the helicopters certainly allow you to fly over terrain, but there's the capacity, the payload capacity is, Ingenuity is carrying 60 kilograms. That's the part where it's harder to do with a flying vehicle. The atmosphere is so thin. Ingenuity's rotors spin at 2,800 RPM. So flying on Mars is like flying at 100,000 feet on Earth. So it's a challenge to get to those payloads. So I think we'll see a mix. They allow you to have certain access, but we're still going to see some rovers, I expect.
And also, if I can ask a follow-up, can you use then Ingenuity with a communication on orbit, or is not an option? The communication system of Ingenuity is too less powerful.
We can't, yeah. So Ingenuity only talks to the rover because partly it has so little power that we conserve it so it talks a relay through the rover right now because otherwise it's a much smaller vehicle and it would require a lot more energy to do that. Yeah.
Sure. Hi, nice presentation. Well, the question is on, generally the way these missions are designed, you guys have had a nice thing where, you always exceed the expectations. Look at Spirit, look at Opportunity, look at Ingenuity. It wasn't supposed to fly for 50 flights. You still have that thing. Coming from an FRC or a field robotics background, demos are tough. Getting robots out there is tough. Getting them to work again and again every day is tough. What's the secret sauce here?
Yeah, I know it is interesting. So one, Earth is always an interesting analog. So it's like, flying, I don't know. I used to, when I was at Pittsburgh. Things work, when you design them for Mars, they work better on Mars than they do on Earth, actually. But at the same time, that is, I think, one of the things that I think is one, we most always say we don't get to fix hardware once it's launched. So the choices we make both in the design and actually a lot of the software is how testable is it going to be? And also, how can we have this term called a leash, at least in the algorithms part, where I know what the navigation's going to do, but as I show the keep and keep out boxes, I want to put a leash on how much I let bound its sort of how much it can make a decision where if something goes wrong completely outside of what I expect, the worst case outcome is still not that bad. And something wrong happens on a regular basis. So all the things you talk about the demos, they do happen. The question is, what is the consequence of it and how do we handle it? Right? And that's, I think, what we do. It isn't that we don't have the issues. Maybe we have a lot less because of the development we go through, and we have a lot of experience from seeing things previously. Everything, we have all these automated checkers for operations that check all these things that could go wrong with the drive. They all came about because something did go wrong with the drive on one of the previous rovers. And so we built this whole system of looking at it. But I think it's mostly that, is having a way in which you contain the risk, both in your overall design. You always ask that question right from the beginning.
How are the helicopters going to pick up the samples? Isn't it possible that they could get covered by dust or shifted around by the wind?
So we did a lot of studies on that. So Mars is a dusty place, and usually, when we do a little, we have a little, we carry a tank on Perseverance that has little nitrogen gas, and we puff away the dust once we abrade surfaces so that it's clean. But very quickly, it gets covered by dust. So it is dust is always moving around. But it's not going to cover those samples to the extent, they're just not going to bury them. also we know exactly where they are. So we've documented in Three Forks where we dropped them based on where we know where the terrain is. So even if, they're not going to based on the studies that we've done, but we would be able to get really right up to them, at which point we should be able to detect them.
I want to follow up on that because, you said, you mentioned how uncertain the helicopters are in their flight. How are they going to find that needle in the haystack when they don't even know where they are most of the time?
Right, so the Ingenuity has a lot of uncertainty, and with the landing, we sort of, it can be tens of meters sometimes off of from the landing site. It's going to be different with what we call, the next helicopters are called sample recovery helicopters, we call them SRH. So the plan is you land about 200 meters from the depot where we're going to land. So they have about that range to fly. The first flights that they're going to do are going to be just mapping. So they're going to fly that area up to where we know in the region and just take images to create a medium terrain map. So we have the global map from orbiters, and we're going to have this map do global localization. Then on that map, they're going to detect features as they go for their sorties. They have to land in an area about a disk around the tube, about 5 to 10 meters, and then we're actually going to drive. So from that point, they just have to land close to it. They drive to the tube, and then the manipulator picks it up. So we're not actually landing on top of the tubes. Yeah. And that's part of the reason why. You could solve that problem jointly, but then we have these brainstorming sessions, and you look at all the crafts of design. There were some wild ones, and some of them did involve, like, even if you didn't land, can you just hop fly? And it's not outside of the space still, but the risk reward made a lot more sense to put some lightweight wheels on. Yeah, go ahead.
Follow-up question about exactly the location of the samples. I guess this rover also have wheel odometry for recording the distance traveled, and you also do global repositioning for the odometry drift, like use a orbiter and you provide some global information, reduce the odometry drift, so you know the exact position.
Right, so we do the visual odometry, but it accumulates some error, and also with the IMU, and also actually we have distance we travel, 5% error in position as we're driving. Once we actually get to the end of a drive, we take an image panorama from the rover, comes down to Earth, and we have a loco team of humans that actually localizes those end-of-drive maps to it. So at the end of a drive, we reduce that uncertainty completely, not by telling the rover it's teleported, because that would change the global, its onboard estimate. We actually just slip Mars under it and change the global map. So our assumption on the ground is wherever the rover is, we've shifted our global map to an understanding of where it is. Yeah.
You mentioned with the helicopters that their chips are just sort of Qualcomm chips and they're not radiation hardened. Has the team seen any issues with radiation causing problems in the processing?
Yeah, that's a great question, because that is one of the reasons why, in the beginning you wouldn't use. So we've seen one guaranteed radiation effect where we had a single event upset. And then there are others where there have been cases where it could have been, but we don't have the data. So we don't know. There have been a bunch. And actually, we have another intern that actually is working on this task where we're looking to use the Ingenuity processor to do global localization for the rover. It's fine for Ingenuity because it was a tech demo, but if you're going to tell the rover it's in a different place than it thinks it is, and you're using that processor, then we do. So we're actually working with another intern. He's working on software-based radiation hardening techniques. So there's, of course, the voting base, but there's other approaches to look at how you can detect them, and at least not use the solution when you detect them. For us, it's different. The advantage with robotics and surface is if you know you detect it, you can choose to come back another day. Why we don't have it on the main computer is also used for landing, and there you don't have another day to come back, right? And so that's why we can do it on co-processors for robotics and not as much on the main computers.
Like you were talking about Perseverance looking a lot like Curiosity, and you've got this very conservative, using stuff that you know is tested. If you could send a mission up with totally new stuff, you could test out anything you wanted, wheels or motors or computers or antenna, what would you be most interested in trying out?
Right. So I think a lot of it is first just putting on multiple co-processors so we're not limited. Because it really, what's advantage of having an independent computer is also when we try riskier algorithm, you're containing it. You're not going to corrupt some other memory and others. I mean, I think it would be really interesting to, in terms of the science that they're interested in, right, like on the missions, of having multiple robots, one, of different forms, like actually a flying robot that can do scouting reliably, because then you can pick what areas you want to go, and we're doing more directed drives. And also sort of vision that, actually LiDAR would be really great, and we're looking at, because they're getting so small, it would be really nice to have. And then be able to combine the information we have from all the different imagers. We have actually 25 cameras if you combine the Ingenuity camera into a model of the world that has the uncertainty built in. Because it's not that we don't have the information, but we do need to combine it. So we spend a lot of time with manipulation understanding what the uncertainty is, because we have to be okay regardless of where in that uncertainty regime the actual falls in. So I think just in terms of having better software and techniques, that's where I'd go. In terms of the hardware, having vehicles that can, one, drive faster, that would be great, as he was saying. I think that would be very useful to have. And then also having the ability to sort of have multiple manipulators, so you can do more things simultaneously, but actually in terms of surface interaction would be really interesting, I think, for the science they want to do.
What improvements are you making to the lander vision system for sample return?
Right, that's a great question. So you know how when we were coming down, detected a hazard, diverted us, but it found two solutions. One was close to the delta, and one was on the other side. The one on the other side was just slightly better, and that's where we ended up, right? When we do with sample return, we're going to do pinpoint landing. So we actually, because we need to land close to the tubes if SRH is going to go there. We can't be 5 kilometers off. And so it's now looking at using the vision. It's going to be much more improved, where we're actually going to be landing in a much tighter envelope, to get to where we want to do. So it's not going to just look at, here's a hazard, let me get to a safe spot. It's going to be like, here's a global map, and here's where I'm trying to get to, and I'm going to land there.
Well, using the Rovers, don't you kind of know already where it's safe to land? Because it feels like you've put a bunch of rovers on Mars, and we know, or we have a decent map. Are you guys clearly going to pick from these maps, but there should be a way to use the prior knowledge of these rovers to sort of scout an area, and then that way you don't, I'm completely just making assumptions here, but it feels like you could somehow use rovers to sort of much more accurately predict and pick these landing spots. Is that what you're doing, or is?
That's exactly what we're doing with Perseverance. So we know exactly where we want to land in Three Forks. That's why we deposited the samples there, because it had a place for it to land and a place. But why we haven't done it in previous missions, because we never wanted to go back to the same place. Because if you're going to go to Mars, each mission has gone to a new, interesting, different place. But this is a different case. We're actually going to go collect the samples. So that's why the helicopter problem is more contained in the lander, because we actually know where we're going to land. But that's why as Perseverance drives, the actual mission could end up at different places. And all of those we're looking at from the perspective of, can we land there, in addition to driving there. So we're kind of like almost going between potential sample return landing site as a helipads, landing sites. We're navigating between them. We have a set of them.
So for the Rover projects like EELS, are there any other robotic plans for underwater robots, like completely under the surface of the ice shelf?
Yeah, actually, I only talked about a few. As I was saying, we have like lots of projects. So there are very many concepts, because the ocean worlds are going to be very interesting. There's actually potential to find, like, here we're looking for ancient signs of life. There could be actually existing life. There's a project we have that's funded. It's called, SWIM, where we have like really small micro robots. There's a mothership. It releases these tiny robots, and they can go into Europa and look for various characteristics. But there are a lot of other. It's still in the stage where we're exploring. And this is why there is a research organization, where what are the possible ways we could do it, and could we do it reliably? Like, that's the important part. If you're going to send a mission there, it's going to take a long time to get there. And so I was just talking to Dave earlier, like the moon and other places, some of these missions, even if they're designed for the outer planets, we might actually have an earlier mission on the moon where we sort of mature the technology so that we can invest in the time that's going to take to go there.
Which other projects in the future are you most excited about and why?
Now, that's interesting. It's like asking me to pick between my kids. But, but actually, I think in general, I like both what we can do with the constraint problem like Perseverance. So I'm actually still involved with, actively with how we're trying to improve the autonomous. I worked on that autonomous science we do at the end and also the localization. But I'm really interested in the future further out, explanatory planetary devices, because we're not going to have exactly the same rovers. They don't even make sense in some of the outer areas, and they have to be fully autonomous. So we really have to get to the stage where we are really excited about. So I think, but at the same time, the moon's going to be a very exciting place in the next decade because we're going to have so many different types of missions. So, I think that's why I wear the two hats. I get to work on a specific project, but also kind of feel like I'm part of all these different projects. So they're all very interesting.
Are there any plans to go beyond Moon and Mars, like on the planets?
Absolutely. So, actually, the decadal survey talked explicitly about going to the icy moons, so Enceladus, Europa, and then all the gaseous giants beyond. So as we start to get commercial stuff happening on Mars, NASA's mission is always the science, and so it's going to continue to be exploring further out planets. So that is kind of, when we are looking at these early concepts, they're all actually much further out as well, looking into those missions. Yeah.
Thanks very much, Vandi.
Thank you.